All right, the last part of 1.1 is we are going to focus on the topics of domain and range. So we're still talking functions. That's this whole section is all focused on functions. Today, domain and range. And those words should sound familiar to you. You have heard about domain and range. Now, before I flip to the next page, if you would be able to describe to me accurately what domain is and what range is, you really don't need to jot anything down on the next page. But if at this moment right now you're sitting in your seat thinking, I know what they are, but I can't quite remember. You probably need to jot down a note for yourself so you have something to look back at. And I am going to simplify this a little bit because we really don't need this whole thing listed after there. But let's talk about the difference between domain and range. Domain is the possible values for the input, and that's the phrase I would put. Possible values for the input, or numbers you can plug into the function. The second part of this, or the independent variable of a function, that is true, and that's about the last time you're ever going to see and or hear the phrase independent variable in this room. And I know you guys have heard it before. It just doesn't come up very often for us. And so I have it on there. You really probably don't even need that distraction in your notes because we don't use the word or phrase independent variable. But it's what we can plug into the function. What numbers are we able to put into the function? Range then is our answers. What possible outputs do we get from that function? And again, with math speak, another way of talking about that is the dependent variable. And that's about the last time you're going to hear that phrase in here, dependent variable. But range is our possible outputs. What answers can I get from that function? A visual that is commonly used is something similar to this, where we've got a function in the middle, we've got numbers heading in, we've got numbers heading out. The numbers heading in would be our domain, what numbers you can put into the box. The function does something to that number, and it spits out a range or an answer. And to me, it always kind of I'm like, well, why can't all my answer just be everything? Well, let me give you a very simple function that you guys know really well, like x squared. What if my function was x squared? And I know everyone in this room can answer this question for me. If I plug a number into x squared, what kind of a number am I always going to get out of it? If I square a number, it's always going to be positive, isn't it? Always. It doesn't matter what kind of number I put in there, it's always going to be positive. So the possible answers, my range, would only be positive numbers. I can't get a negative number from this function. It would never happen. Okay? So there's an example of something that would have a restricted range. But today we're focusing on the domain part of it. This next page is something that I'm going to refer to like daily or every other day for the rest of the semester, and that is our domain restrictions. We have 3 of them today that we are going to add. Later on in the semester, we'll add one more type of function that has a domain restriction, but these are kind of your 3 basic ones. The first type of function that has a domain restriction is a fraction. If we are looking at a fraction, specifically a fraction that has a variable in the denominator, okay, it has a domain restriction, and here's how you're going to find that restriction. You are going to set the denominator not equal to 0. Why? Because we're figuring out what x can't be. The denominator cannot equal 0 in a fraction. So here's a very basic example of what that would look like. 3 over x plus 3, that's a fraction. It says take the denominator and set it not equal to 0. Solve for x. X cannot equal -3. That's what's called a domain restriction. If they ask me to actually identify the domain, we've got one more step to do, and that's to write it in the interval notation. So this is your restriction. So what would our domain look like? Well, I'm going to go back to that number line idea that I've been using a lot in here. If I were to show this idea on a number line, not being able to equal something is an open dot, right? So if it can't be -3, I'd have an open dot at -3. But it can be everything else, right? It can be anything to the left of this or smaller than -3. So I would have an interval that would describe all of those numbers, and that would be from -infinity up to -3. Now it can't equal -3, so I use that parentheses. It can also be all of the numbers bigger than -3. So from -3 up to infinity. And what you're going to notice is I have two intervals describing my domain. -infinity up to the number it can't be, the number it can't be up to infinity. That's going to happen when we have a can't equal or not equal to, is that you're going to end up with one more interval than you have numbers it can't equal. It couldn't equal one thing, so we had two intervals as our answer, showing the break at that number. All right, our next domain restriction is if we are looking at a radical. Now, this is specifically a radical with an even root, a square root, a fourth root, a sixth root. It does not apply to odd roots. It is not a cube root, fifth root, seventh root. We don't see those, but I mean, it is not an odd root. It is even roots only, and that says that we are going to take what is under the radical. And remember, we can only square root positives or 0, and that's why we are going to take what's under the radical and set it greater than or equal to 0. Can't be negative, right? So I'm going to take what's underneath my radical in this basic example here. Say it's greater than or equal to 0, solve for x. And find that x would have to be greater than or equal to 5. When we describe our domain, if they ask us to describe the domain of the function or state the domain of the function, we will always write it as an interval. So now we did that already. X is greater than or equal to 5. We know, again, for my visual people here, I'll do it on the number line. Greater than or equal to 5 is going to include 5, and numbers bigger than 5, so from 5 up to infinity. And then again, this symbol right here, the or equal to, is what's going to make me put a bracket at the 5, include 5. Our last possibility basically combines these two things. It's a fraction and a radical, specifically a radical in the denominator of our fraction. Now, what I want to point out is these two are frequently confused for each other because look how close they are. Same words. Set the part that is under the radical, and then one of them is greater than or equal to. If it's in the denominator, it can't equal 0, so just greater than 0. So in my basic example here, I'm going to take that x plus 4, greater than 0 only. X has to be greater than -4. Writing that in my interval notation. It can't equal -4, but is everything bigger than that. So again, our interval will go from -4 up to infinity, and because it is not equal to -4, we're going to use a parentheses there. Questions? So when we are asked to state the domain of a function, I actually, instead of going to the domain, I go to the restrictions, and I'll just tick off that list each time. Is it a fraction? Is it a radical? Is it a radical in the bottom of the fraction? And if it is, we follow those rules to figure out what our restriction is. But what happens when I go through that list? Is it a fraction? Is it a radical? Is it a radical in the bottom of the fraction? And my answer is no, no, no. Okay? And that's what we're going to see on this next page. What if it doesn't match one of our restrictions? I go through my list. I'm looking at these two options up here. F of x equals x squared minus 2x plus 3. F of x equals 2x minus 7. And I'm supposed to think about its domain, and my restrictions are, is it a fraction? Nope. Is it a radical? Nope. Is it a radical in the bottom of the fraction? Nope. Okay, well, that means that it doesn't have a restriction. So if you think about what that phrase means, no restriction means everything, right? So how do we show that in numbers? If we are talking every number, first of all, one of the phrases you've probably heard over the years is all real numbers. Right? Have you heard that phrase before? All real numbers. How do I show that in interval notation? Well, all real numbers in interval notation, what would be the smallest real number? -infinity. And what would be the biggest real number? +infinity. Okay, so if I want to say that there aren't any restrictions, guys, people get hung up on these questions because they feel like they should be doing some work, because we just did some work on the last page to figure out the restriction. But if there aren't any restrictions, that's your domain. Negative infinity to infinity, move on, right? Nothing to do, it's all real numbers. Any questions on that? All right. But let's look at the ones that do have restrictions. So our examples from here on out are just practicing the ones that do have restrictions. So all of ours are going to have the same directions at the top. State the domain of the function. Our first example is g of x equals square root of 3x plus 2. So I go through my options. Square root of 3x plus 2, is that a fraction? No. Is that a radical? Yes. So we go back to that little chart we just made and find where it said radical. And radical said, take what was underneath the radical. And this is a chart you're going to need to know by heart. Take what's underneath the radical, greater than or equal to 0. Cannot be a negative, but it can be 0. So I take that 3x plus 2, greater than or equal to 0, solve for x. X is greater than or equal to negative 2/3, and we will always finish out our problems by writing it in interval notation. Again, if you like the whole writing on a number line at this point to help you with your interval notation, do that. It can be negative 2/3, and then bigger than negative 2/3 would head this direction, so my interval is going to be negative 2/3 to infinity. And remember, this symbol, or equal to, is why I'm going to put a bracket at the negative 2/3. We are including negative 2/3 as part of our set. That's the only one I have for our radical example. So before I move on, are there any questions? All right. Next one, same direction, state the domain. This time our function changes. H of x equals 3x plus 1 over x minus 2. And we go through our three options: fraction, radical, radical on the bottom of the fraction. We are looking at a fraction. So we glance back at our table and it says if it is a fraction, we take what part of the fraction? Bottom, the denominator. That's the key in fractions. The bottom cannot be 0. We say that the bottom cannot equal 0. Solve for x. And then this is the one that's new to us today as far as how do I go from that to writing my interval notation. Remember, when it is a not equal to, that you're always going to have one more interval than you have numbers. I have one number, so I should have 2 intervals when I'm done with this. And again, if the number line helps you do that, can't be 2. It can be everything below 2, so negative infinity up to 2. It can be everything bigger than 2, so 2 to infinity. Okay, if there's just one number, it will always just go negative infinity up to that number up to infinity. Before I move on from this one, I just want to address, in case it's bothering anyone, does it bother anyone that there's a variable in the numerator and I didn't talk about it at all? There is a variable in the numerator. I understand that. But think about the numerator of a fraction. Is it okay to have something like a fraction like 0 over 3? Yeah, negative 1 over 3. Yes, 1 over 3. It doesn't matter what we put in the top of a fraction. The only thing we can't have in a fraction is something like 3 over 0. I can't divide something into 0 groups. Okay, so that's why we care about the denominator. The numerator does not ever have any impact on our domain, so you don't ever have to worry about the numerator, whether it has a variable or not. All right. Sticking with our idea of fractions, I want to take this one step more complex. So we're still looking at a fraction, so we're using the same domain restriction rule, and that is on a fraction, the denominator cannot equal 0. And you'll notice the denominator this time, we've got 3t squared over t squared minus 1. The denominator is a quadratic. This is why we did our warm-up today. T squared minus 1 cannot equal 0. I need to know what values of t that actually is. So if it's a quadratic, we would factor and solve for t. That is a difference of 2 squares. Remember, that's going to be 1 positive, 1 negative. Square root of t squared is t. Square root of 1 is 1. So t plus 1, t minus 1. Set each of those equal to 0. Not equal to 0 to solve. And I find out that t cannot equal negative 1 and t cannot equal positive 1. This, again, is going to be a unique one. We have not done an interval notation yet where we have two things that it can't be. But if you remember, I said we're always going to have one more interval than the things it can't be. So if I have two numbers it can't be, our answer is going to have 3 intervals. All right. So how does that happen? First of all, if you are a number line person, make sure you put these in the correct order. Should go small number first, big number second, negative 1, then 1. It can't be negative 1. It can't be positive 1, but it can be everything else. Well, everything else happens in 3 locations. Negative infinity up to negative 1, lower than our smallest number, is one of our intervals. Then the next interval is the one that everyone always forgets if you're going to forget an interval. It can be any number between those two as well. This guy gets forgotten all the time, but the interval from negative 1 up to 1 would include things like 0 and a half. All of those work in this function. And then the last one from 1 up to infinity. So let's talk about the pattern here. If you're not a number line person, it is always going to follow this same pattern, and that is this. From negative infinity up to your smaller number to big number to infinity. Every time. Okay, that's never going to change. So you can follow that pattern, or you can draw yourself a picture. Don't forget the middle guy. Always one more interval, then you have things it can't equal. The next one is just like the one we just did, so I'm going to let you guys try this one at your tables. Get all the way to your interval notation for your answer. All right, let's go ahead and check how we did. Just like the last one, we're going to take the denominator, because that's all we care about in a fraction. Say that our denominator cannot equal 0. This is a quadratic, so to solve for x, that tells me I need to factor. Factors of negative 18 that add up to 3, we should have picked positive 6 and negative 3. Make sure you get to that next step of actually solving. Common mistake is people just take the numbers that are in the parentheses. You actually have to set it equal to solve, 0 to solve. So I get 2 answers. X cannot equal negative 6. X cannot equal positive 3. I should have 3 intervals when I'm done with this because I have 2 numbers that x cannot equal. Cannot equal negative 6, cannot equal negative 3. So my 3 intervals are the lowest end, negative infinity up to negative 6. Between my 2 numbers, negative 6 to 3. And then for my bigger number up to infinity, 3 to infinity. Again, parentheses everywhere because we're not including any of those numbers. Any questions on the fractions, especially with those quadratics in the bottom? And our new way of interval notation from not equal to. Okay, we have not seen an example of the last type of restriction, so we'll just add one of these into our notes so we do have one of our radical in the bottom of our fraction. See if you can remember what that was off the top of your head. If not, glance back at your table that you wrote down of your 3 different types of restrictions. What do we do for this one? Or think about what kind of numbers can be there. If it's a radical, that means it has to be positive. It's at the bottom of the fraction, it can't be 0, right? That is what should lead us to taking what's underneath our radical and saying that it is greater than, only greater than, 0. Why not equal to? Can't make the bottom of my fraction 0, right? Cannot equal 0. Solve for x. and write my interval. Numbers bigger than 3/2 would go from 3/2 up to infinity. Open dot because it is a just greater than. And I don't care if you wrote it as 3/2, 1.5, 1.5, that's all the same thing. Any questions on that? Okay. On this next one, I want you to look at this function up here. F of n equals 5n plus 50. This should look like the ones we saw at the very beginning. If I handed you this function and we ran through our options, is it a fraction? No. Is it a radical? No. Is it a radical in the bottom of my fraction? No. So does it have a domain restriction? No. So what would you tell me the domain is? All real numbers, negative infinity to infinity. Now let's talk about what this function actually represents. That's what I would have said the domain was based off of the function. But let me give you a situation. This function represents this. Groups get paid for selling tickets to the football game. They get $50 for just doing it. And then they get $5 for every ticket they sell. $5 for every ticket they sell. So n represents the number of tickets we're going to sell. Okay. Well, based off of the function, that says I can sell up to negative infinity tickets. What's actually the smallest number of tickets I could sell? 0, right? Actually, I could sell 0 tickets. Now, hopefully I sell more than that to our football game, but I could sell 0 tickets. What's the biggest number of tickets I could sell? Infinity, right? Because if I drive up there, I can fit infinity people in our stadium, can't I? No. I can sell the capacity of our stadium. I don't know what that is. But I could sell the capacity of our stadium. Unless I'm an airline, then I can sell more than that because they always oversell their planes, right? But capacity, I don't know what it is, but that's the biggest number of tickets I can sell. Different than what the function actually told me for a domain, but the situation gives me a domain restriction, doesn't it? What you guys are looking at in play here is what is called relevant domain. Relevant domain. Relevant domain refers to a domain restriction that happens because of the situation, not because of the function itself necessarily. The other example that I have up here, you really probably don't need to put in your notes, but these are good examples of things that would have relevant domain. Piecewise functions, if I look at each of the pieces, are where my domain restrictions could come from. But if you look at these, none of those are fractions, radicals, or radicals in the bottom of a fraction. So initially looking, it would say no domain restriction. But that piecewise function is representing how much you are going to pay for your electricity at your house. And the electricity at your house you pay for based on how much electricity you use. How many of you have parents that tell you to turn off the lights in the room when you leave it, right? Or shut the door because we're not trying to air condition the outside. Or to turn off the TV when you leave the room. All that because you're paying for it when you use it. But we would never use less than 0 amount of energy in our house, would we? 0 is the least amount we could ever use, which is why you'll notice that this starts at 0. Okay, so the relevant domain on this one, again, not from the function. There's no restriction on those functions. But the situation, we're not going to use less than 0 amount of energy in our house. So that's where that restriction comes from. Any questions on relevant domain? All right. Your assignment tonight is out of the book. We actually just kind of covered 2 different sections. So you have 2 different pages, P13, which is the one that comes from the very beginning of the book, and then just normal page 10 is the other half of that. Go ahead and get that written down, and then after that, we're going to talk about that homework quiz you guys took yesterday.